In this video, we are going over the background for Lab 2, which is titled Measurements. Let's first state what are the experimental goals for the following lab. Students that perform this lab will properly learn how to use metric units for conversion problems. There are also units in the metric US and the US system that are going to be taught in the process. The students are going to learn how to state the correct number of significant figures in measurements. They will learn how to state the correct number of significant figures in conversion problems. They will correctly report measurements from a ruler. They will learn how to also correctly report a measurement from lab equipment that measures volume. When we are in the laboratory, all of us are scientists, and understand that as scientists, we're going to use measurements that are based on a universally accepted standard. That standard is the metric system. And in the following slide, we can see a selected number of measurements, followed by what are the basic units and their abbreviation. You can see that some of the ones that are present here will be utilized in this lab and labs throughout the semester. Just to state a few. As we can see, we have a measurement of length, and length, its basic unit is a meter, and the abbreviation is a lower m. When we take a measurement of mass, the basic unit for it is grams, and the abbreviation is a small letter g. And lastly, as you can see for volume, we have units of liters, and we can see that the abbreviation is an uppercase L. We also have here time, temperature, energy, and amount of substance. And throughout the semester, we're going to see some of these measurements taken or being utilized in problems throughout the course. When we're talking about measurements, one of the important features in the metric system is that there are prefixes that can be utilized with it that is going to increase the value of our basic unit, or it can decrease the value of our basic unit. So when these are utilized, we can see how our metric system gets into larger amounts or smaller amounts. In the table, in this slide, we can see how there are prefixes for making the number smaller, and they go from deci to yocto. All of these that you see here, deci, centi, milli, micro, nano, pico, femto, atto, septo, and yocto, make the measurement small. Now, there are prefixes that can make that metric unit larger, and they go from deca all the way to iota. So this makes the measurement larger. Now, one of the things that we can observe here, and before I proceed, as you can see, they're deca, hecto, kilo, mega, giga, tera, peta, exa, zeta, and iota. When we can see here is that all of them are related to one another by a factor of 10. And you can see in the third column their decimal value. We can see in the fourth column their scientific notation. Okay, and you can see also the colloquial. Understand that this prefixes is just to illustrate that the prefixes actually are more extensive compared to the ones that we talked about in lecture and are given in table 2.4 from the textbook. Now, let's understand that whenever we have measurements, we can actually utilize a conversion factor to convert from a unit given to a unit needed. As you can see, a conversion factor is going to be a number or a formula you need to convert a measurement in one set of units to the same measurement in another set of units. So in the lab sheet for lab 2, we can see that there is a table for unit conversions for length, energy, mass, pressure, temperature, and volume. And this is how you utilize these conversion factors for conversion problems. Let's read the following example. A full marathon race consists of 26.2 miles. If you complete a full marathon race, how many kilometers would you have run? Well, the first thing that we need to state is what is the relationship between the units given, and the unit given is miles, and the unit needed, which is kilometers. When we look at our conversions, we can see that there's a relationship between kilometers and miles, where 1 kilometer equals 0.62137 miles. There's also another conversion in which gives you 1 mile equals 1.6093 kilometers. You can use any of the two in order to accomplish this problem. Now, utilizing dimensional analysis, how we're going to do the problem, and understand that there's other methods. You can use cross multiplication. Use the method that you feel more comfortable with. I'm going to teach you dimensional analysis because we use it throughout the semester. First, we're going to write the measurement given, which is 26.2 miles. Then, my conversion factor, I'm going to write as a fraction. And again, you can use any of the two. Let's say that I'm going to utilize the 1 kilometer equals 0.62137 miles. So, in dimensional analysis, what I can do is that this conversion factor, I can actually turn into a fraction. And the way that I do that is that I'm going to put in the bottom of the fraction the unit that matches the unit given. So in the bottom of this fraction, I will write 0.62137 miles. And on the top, I'm going to put what it equals to, 1 kilometer. The units of miles will cancel. And in order to solve the problem, I have to do 26.2 times 1. And I'm going to divide that by 0.6237. The result of this is going to be in kilometers. So when I do that, 26.2 times 1, and I divide it by 0.62137, the result in my calculator display is 42.1648937. Now, one thing that we have to keep in mind is that when we're doing a conversion factor is the number of sig figs that we have in the measurement given. Here we have 3 significant figures. Because during our conversion, we are dividing and multiplying. The rule states that we are going to, even though our calculator display shows us many digits, that we're going to show that final answer with rounding to the same number of significant figures as the measurement given. So in this case, we need to round those digits to 3 significant figures. And our final answer for this problem is going to be 42.2 kilometers. One of the things about measurement is that there's always error in measurements. There is no such thing as an exact measurement. In fact, there's actually two types of experimental errors that can happen when you are in the laboratory. Understand that those two types are gross errors and scientific errors. Gross errors make allowance for the intentional failure to notice or to do something by a scientist. So let's say that you are in the lab and after you measure some of your sample, there is some spillage as you're pouring it in the next glassware that you need to utilize to do the reaction. Let's say that there's names of chemicals that are very close. So for example, sodium bicarbonate and sodium carbonate are not the same thing. And you can correctly use one over the other. Or let's say that you are trying to do a calculation and you make a mistake during calculations. All of those are going to be considered gross errors. At times, students utilize the term human error, but when it comes to the laboratory, those human errors, quote unquote, is what we called gross errors. On the other hand, we also have scientific errors. And when it comes to scientific errors, they actually have two types. They can either be systematic or random. When it comes to systematic errors, they arise from defects in the measuring instruments or from mistakes in the application of a technique. In the next video, we're going to talk about the technique of how to correctly read volume in glassware. And let's say that, just to introduce these concepts, you are reading volume in a particular glassware and you incorrectly read the volume of the liquid by not paying attention where the curvature of the meniscus is. That will be a type of systematic scientific error. When it comes to random scientific errors, those can result from unidentifiable sources and it varies unpredictably from one measurement to another. There are situations when you are in the laboratory and, for example, the ventilation system may be blowing a lot of air and changing the mass of the substance just because the air circulation is not the same. That is a random error because that just came from the environment and it could vary from day to day. Understand that scientific errors, it doesn't matter if they're systematic or random, they have effect of reducing not only the accuracy but the precision in a measurement.